Okay, so back to thermodynamics. Last time we talked about the new variable entropy. Entropy, we said, is a measure of the spread of energy, which is a pretty good summary, but the real definition is a measure of the number of different ways that energy can be stored in a system. So we're talking about energy distribution within a system. So if we look at the graph on the right, if I tell you that one of these distribution curves is for a hot gas and the other distribution is for a cold gas, which curve is which? Hopefully you recognize that speed's on the x-axis, and so a gas that has more molecules of higher average speed is going to be the hotter gas. The smaller average molecular speed of the gases is going to be the cold gas. So the red one is a hot gas, the black one is a cold gas. So the hot gas has a bigger, broader distribution curve. There are more ways that energy can be stored in a hot gas. So the hot gas has a higher entropy value. So talking about entropy things, there's an important law of thermodynamics, the second law of thermodynamics, that we will talk about quite a bit with regards to entropy, because this second law is all about entropy. It says, for any reaction to occur naturally, the entropy of the universe must increase. For any spontaneous change, the entropy of the universe must increase. That is always and forever true. But wait, you said last time this reaction has negative entropy and it can happen. That's true. So a reaction is a small subset that we're going to call the system. So a system reaction can have negative entropy, but there's something else that has to be considered, because the universe entropy must always increase in order for a reaction to happen. So there are three parts that we have to consider: the entropy of the universe, the entropy of the system or our reactions, or the entropy of the surroundings. So if a reaction has a negative entropy value, the surroundings must increase by more than the system decreased in order for the delta S of the universe to be positive, because the second law says delta S of the universe has to be positive for a reaction to happen, period. No ifs, ands, or buts about it. So if we look at a little quick system, if I say the brick on the orange, the brick on the left, the orange one, is the hot brick. It's at 400 Kelvin. This one is the hot brick. This is the cold brick. It's 200 Kelvin. Hopefully you know that when you put those next to each other, the hot brick will cool down and the cold brick will warm up, because heat is being transferred from the hot brick to the cold brick. As it turns out, when heat is transferred, so is entropy. So if you take a look, this says Q of 3,000 joules. Q is a measure of heat energy. Q and H are related. Q, heat, and enthalpy are related. So we'll use those somewhat interchangeably for now. So when heat energy is transferred, so is entropy. So if you look at this crazy little cartoon down here, we have these little Q guys walking out of the hot brick and going into the cold brick, and their S suitcase size is increasing. When heat is transferred from one thing to another, entropy is also transferred. So what does that matter? How do we do this? Well, we said the second law of thermodynamics says for any spontaneous change, the entropy of the universe must increase. So entropy of the universe is comprised of entropy of the system and entropy of the surroundings. But the entropy of the system can be defined as the Q of the system divided by temperature. So the heat of the system divided by temperature. Well, that's great. So what? Well, we also need to know the entropy of the surroundings. But the entropy of the surroundings is not so easy to measure. So we're going to take advantage of a couple of things. If you know that heat absorbed by a system has to have come from the surroundings, or heat exiting the system has to go into the surroundings, we can take advantage of this property, saying for every heat that's transferred, the signs between the system and surroundings will be equal and opposite. So any heat going into the system has to come out of the surroundings. Any heat coming out of the system has to go into the surroundings. Equal and opposite, they must be. So if we are trying to find delta S of the surroundings, that says we can take advantage of knowing this equal and opposite property. So we can say, instead of putting Q of the surroundings here, we can put negative Q of the system. So delta S of the surroundings is defined as negative Q of the system divided by T. So as I said a minute ago, we're going to say Q and H are kind of similar. There's a little more information included there that we're not going to get into, but we're going to change that Q into an H, and we're going to say delta S of the surroundings is equal to negative delta H of the system divided by T, because those variables are something we will see again and again and again throughout this material. So we said before, and we will say again, in general, exothermic reactions tend to be spontaneous. Why is that? Well, of course, it's all about the second law of thermodynamics. The second law says, for any spontaneous change, the entropy of the universe must increase. I've said that a few times. Hopefully you'll get that you need to know that pretty well. Delta S of the universe must increase for any spontaneous change. So if we look at a couple of systems, in this one, we have some sort of system, which is our chemical reaction, and heat is leaving it. So if heat is leaving the system, that reaction is endo-exo. Yeah, that reaction is exothermic. So delta H is negative. An exothermic process, heat is leaving, delta H is negative. So when heat is leaving, as those little crazy cartoon guys said, when heat leaves, entropy leaves with it. So the entropy of the surroundings will increase as that heat leaves. So the entropy of the surroundings will be positive. So we can also say that by saying, this is what we just said on the last slide, the last little conclusion we made. If this value is negative, negative times a negative, this gives me a positive value. So delta S of the surroundings will be a positive value. Delta S of the surroundings is positive. So if delta S of the surroundings is increasing, in order for the reaction to be spontaneous, delta S of the universe must increase. So the system, this is going to be a negative value because the system is losing entropy. But the surroundings is gaining more entropy than the system is losing. So this makes delta S positive. In general, exothermic reactions are spontaneous because exothermic reactions always cause delta S of the surroundings to be a positive value. Exothermic causes delta S of the surroundings to be positive. Endothermic. Let's talk about endothermic. Endothermic has heat going into the system, so delta S of the system will be positive, but delta S of the surroundings will be negative because when heat exits, entropy also decreases. So this delta H is a positive value. It's an endothermic reaction. So delta H is positive, positive number times a negative number. Delta S of the surroundings is going to be negative. The entropy of the surroundings is decreasing. Delta S surroundings is decreasing. So if delta S of the surroundings is decreasing, that's not great. That's not going to lead to many opportunities for delta S of the universe to be positive. The only way that an endothermic reaction can be positive is if the system entropy is increasing by more than the surroundings entropy is decreasing. Yeah, real confusing, I know. The only way an endothermic reaction can be positive is if the system entropy is increasing by more than the surroundings entropy is decreasing. This one, the surroundings entropy is positive. The system is going to lose heat. The system is going to lose entropy, but it's usually not a lot because it's a small value. The surroundings changes drastically. So let me pause this 1 second to write out a few things. So if we're talking about the second law of thermodynamics, there are a few options for what signs the second law of thermodynamics can give me. Remember, delta S universe has to be positive. That's what the second law says, period. If we say delta S of the system has to be, no, that's not what I want to say. Start over. We can change delta S of the surroundings to be negative delta H of the system divided by T. So we can look at a couple of signs to say whether a reaction will be likely or not. Before we go through all the math of what's likely and not, let's just look at the combinations of signs. If delta S of the system is positive and delta H of the system is positive, positive plus a negative, I don't know if that's going to be spontaneous or not. If delta S of the system is positive, delta H of the system is negative, is that reaction going to be spontaneous or not? Positive plus a positive, that is always and forever going to be a positive value. If we're looking at the other way, where we have a negative delta S system and a positive delta H system, I'm just bringing down the remainder of the formula. Negative plus a negative, that is always and forever going to be a negative value. Do we like a negative delta S universe? No. One more scenario, if we have a negative delta S system and a negative delta H system. These are possible combinations. Negative plus positive, I don't know if that's going to be spontaneous or not. So if we look at our four possible values here, this one, we said delta S universe is always positive. So this reaction is always and forever spontaneous. We said the very next one, where delta S of the system is negative and delta H of the system is positive, that is never spontaneous. But these other, the top and the bottom, we don't know if they are or not. Turns out they're temperature dependent. Hold that thought, we'll get back to it. Let's go back to the PowerPoint real quick. So, if we get back to where we were and we consider this reaction up top, if you look at the number of molecules in the reactants side and the number of molecules in the product side, the entropy of that reaction is increasing because you're gaining more molecules. You have more disorder in the products than the reactants. So delta S reaction is positive. If I tell you that this delta H reaction is also negative 100 kilojoules, that's endo or exo? Yep, exothermic. So delta H of the reaction is exothermic. Delta S is positive. Delta H is negative for the reaction. So if you combine all that together, that tells you delta H of the reaction is negative. So delta S of the surroundings is positive. Positive delta S reaction, positive delta S surroundings, positive delta S universe, always and forever. If you went back to our original papers, that's when delta S is positive, delta S of the system of the reaction is positive, delta H of the system of the reaction is negative, always and forever spontaneous. The other one to consider is when we have a lot of moles becoming fewer moles, delta S of the reaction is definitely negative, definitely negative. If I tell you that that reaction is also an endothermic reaction, a positive delta H, that endothermic reaction is going to make delta S of the surroundings negative. And when delta S of the surroundings is negative, delta S of the reaction is negative, that is never, ever, ever a positive value. So those are the ones that say, those are the conditions that say always or never. What about when it's not always or never? That top one, we have a lot of molecules becoming fewer molecules. So our delta S of that reaction is negative. But if I tell you that reaction is losing 450 kilojoules of enthalpy, that's an exothermic reaction. Exothermic means negative delta H of the reaction. Negative delta H of the reaction means positive delta S of the surroundings. Positive delta S of the surroundings, negative delta H of the reaction, delta S of the reaction. I don't know if delta S's universe is positive or negative. It's temperature dependent. This says that delta S of the surroundings has to be bigger than delta S of the reaction in order to be spontaneous. One more. Oh, yep, sorry. Delta S of the surroundings is all dependent on delta H. So delta H is the deciding factor here on whether this reaction will be spontaneous or not. We would say this is an enthalpy-driven reaction. One more. So if I'm going from few molecules to a lot of molecules, delta S of the reaction is positive. I'm creating more entropy in the products. If I'm telling you it's an endothermic reaction, then delta S of the surroundings is going to be negative. So delta S of the surroundings is negative. Reaction is positive. I don't know the sign of delta S universe. I need to know the magnitude of these two things. I need to know that delta S of the reaction is bigger than delta S of the surroundings in order to call this reaction spontaneous. So if the top one we said is enthalpy driven, you got it. The bottom one is entropy driven. So we will talk more about enthalpy, entropy, and another new variable in our next lesson.